Alright guys, I gotta say I'm a little bitter here because I just did all of the notes, but my computer camera shut off after the first example. So I was talking to myself for like 10 minutes, which is super cool. Had to print out a new copy, start again. Alright, I'm not bitter. Well, I am bitter, but I am capable of moving on. There's 2 copies of the old one. Okay, so example 2. A researcher claims that more than 30%, alright, so P is greater than 30%, and the opposite is P is less than or equal to 30%. And for this one, I think I decided we were going to do the calculator and rejection regions. We're going to need all of our data. N is 150. P, that's just what our claim is. It's 0.3. Q is 0.7. P hat is 0.38, says right here. And because I know that we're using our calculator, I know that in real life you usually don't have the percentage first. You have how many people said yes to whatever you're talking about. So I'm just quickly on my calculator going to do 0.38 times 150 and find out that the N is 57. Or not N, but the X is 57. So there are 57 people who would have said yes. 57 divided by 150 is 38%. And then our alpha is 0.05. Alright, since we're doing rejection regions, I should probably draw them. It is greater than or equal to, it's a right-tailed test. Let's see, I'm going to look on page A16. Which means that I'm going to look up the area 0.95, because remember that it always reads to the left of that line, and this is 0.05 over there. So if I look in my chart, 0.95 is right about there, halfway between these two. So that is 1.645. Alright, I'm not going to use that formula. That is totally empty now because I had to start over. But anyway, it was what, P hat minus P, etc. And I'm not going to use that because this time I'm going to use my calculator with rejection regions. So here's how you do it. You go to Stat and then over to Tests. Now a Z-test and a t-test, that would be like a z-test would be if you knew your population standard deviation and you were testing a mean. A t-test is if you didn't know your population standard deviation and you were testing a mean. The 2 sample ones you can ignore for right now, that's chapter 8. And the 1 sample proportion, that's the one we want right now. So let's see, our claim is 0.3, our X is 57, our N is 150, and then it is definitely a greater than test. I'm going to choose to have it draw it for me. Normally if you just hit calculate, it'll just tell you a z-score and a p value to compare to your alpha, but instead I would have it draw it because it looks prettier. And it makes more sense to me. The 2 sample stuff is what's going to be showing up in chapter 8. That's where you compare 2 populations to each other. Okay, so there is a beautiful bell curve, and my z-score is 2.14. It says that on the bottom right corner. So 2.14 definitely hits in that rejection region, so I'm going to reject the null, and in this case I'm going to accept the claim that all that stuff. Not going to write it for a 3rd time because after all I had to, this is what I do every day. I make the notes and then I do a trial run where I try it out myself, and then I do it with you guys, which apparently didn't work last time, so now I'm doing it for the 3rd time. Super fun. Okay, example 3 and example 4. This time, for example 3, we're going to use p-values. Remember, the p-value is when you're comparing area to alpha, and we're also going to use a table. And for example 4, we're also going to use p-values, but this time we're going to have the calculator do it for us. So we're going to start with p-values in a table. Okay. H sub O, H sub A. Let's see, a researcher claims that 86% of college graduates say that their college degree has been a good investment. I would say mine has been. Otherwise, I wouldn't be able to be a teacher and be doing this amazing long-distance learning. Now it says it claims that 86%, that is an equals to. So if it just says that it believes or that the claim is or that it is a certain number, essentially, then it's just an equals to. This is a two-tailed test. These bell curves I'm drawing are getting more and more pathetic. We're going to use a table. So again, that's A16. Okay. I'm going to write down all of my data. N is 1,000. P is 0.86, which means Q is 0.14. And we can definitely do this problem because N times Q is definitely bigger than 5. P hat, I don't even need to know for this one yet. Guess I do. So X is 845, which means P hat is essentially 845 yeses out of 1,000, which is 0.845. And then we're comparing that to an alpha of 0.10. Okay. Next up, we have to do that formula, which is p hat minus p over the square root of pq divided by n. And if you do all that math, it is 0.845 minus 0.86 over 0.86 times 0.14. This is all in a square root on the bottom, divided by 1,000. You can tell that I've done this many times. That gives you a z-score of negative 1.37. This is 6. And then if you look up negative 1.37 in your table, negative 1.37 is 0.0853. So 0.0853 is how much is just in one of the tails. But if you remember from that p-value lesson, you've got to multiply a two-tailed one by 2, which gives us a p-value of 0.1706. That's the p-value. And I'm not just going to call it p because we've already got a p in the problem. So that means that our p-value is greater than alpha. And since that's the case, if it's greater than alpha, essentially it means like it's not in the rejection regions, it's in that null. So we're going to accept the null, which in this case was the claim. So I'm going to accept the null and the claim that 86% of college graduates say that their degree was worthwhile. Okay, last one, example 4. A research center